So good morning, everyone. Thank you so much for being here today. We're very excited to have Alex here. She's going to be speaking about surviving extreme temperatures in space. So it's going to be a really, really fun session. Just before we get started, teachers, if you wouldn't mind just popping in the chat how many students are in your classroom, just so that we can know. And then throughout the presentation, excuse me, if you have any questions, please feel free to go ahead and put them in the chat box, and we'll get to as many of them as we can at the end of the session.
I want to hear about the family situation. One sec.
Sorry, teachers, please make sure that you are muted, just so that we are not getting feedback from your classrooms. Just
we turn around and face the front, please.
Second. There we go. Okay, so I'm going to go ahead and hand it over to Alex. At the end of the session, I'm going to have a few feedback forms that I'll pop in the chat that we would love for you to fill out. But for now, let's hand it over to Alex.
Okay, good morning, everybody. I'm just going to share my screen, if this is working. Okay, I hope you can see this. So my name is Alex Davis. I'm an engineer and I work at a company called RAL Space. And we're going to talk a little bit about thermal engineering, which might be a new word for you, but don't worry, we're going to cover it all. So I'll start with RAL Space. RAL Space is a company which does lots of space testing. So we're based on the Harwell campus in Oxfordshire, and this is a photograph of the Harwell campus. I hope you can see my mouse because I am going to be pointing to things. RAL Space occupies this building here on the Harwell campus, and we have lots of big space test chambers in that building. And we also occupy at the back here another building, which is, you can't see very well, but essentially we have lots of space test chambers. We've got big ones, we've got small ones, we've got ones you can fit entire satellites into, or ones you can just fit little circuit boards into, so you can test components as well. We're based on the Harwell campus. We have about 330 staff, and we call ourselves the National Space Laboratory. And the reason we call that is because we're government funded. To give you a tour of the Harwell campus, we also have in the bottom left corner, there's a white coloured building with rainbow coloured windows. And this is one of the many buildings that the European Space Agency has around the world. We also have this circular shaped building. It's called the Diamond Light Source. And they have some very strong beams of light that you can use to look at things like crystals very closely. At the back, we have Medical Research Council, and across the road from that, Public Health England. You can't see them very clearly on this photo. They're very important right now as well because of the pandemic. So this is a very busy science-based campus for lots of different science happening on here. And RAL actually stands for the Rutherford Appleton Laboratories, so that's us. So what does RAL Space do? We have some photographs here. Well, some of them aren't photographs, some of these are computer generated, but we have some pictures here, and I'll talk through them. We've got on the top right corner, we have a picture of some satellites orbiting Earth, and you can tell it's Earth because it's got all these nice white fluffy clouds. So satellites that orbit the planet will be doing things like measuring weather systems, or measuring the temperature of the ocean, or measuring land use. This is all very important for understanding the weather or climate change. So these are important satellites for us. This is another picture of a satellite. This one is actually orbiting the sun. If you can recognize that, is the sun in the background there. This is the bottom right photograph I'm talking about. And it's important to monitor the sun as well, because it affects everything that happens on this planet. Sometimes the sun will emit a large amount of very hot gas called plasma into space, and if that goes into the direction of Earth, it can affect things like our communications satellites. So we've got to monitor this and make sure everything is safe when these sorts of events happen. This top left photo is actually a diagram of the James Webb Space Telescope, which the goal of this telescope is to look as far as it can into the depths of space and look at very, very old, distant galaxies and understand how galaxies have formed and how stars have formed. So this is more understanding the universe kind of satellite. So there's all these different types of satellites, lots of different functions, and we have a hand in how these get made. So on the bottom left picture, we've got an actual photograph, which is of one of our space test chambers. And this thing is huge. You can see there's people stood up in here doing their work, and they don't even reach the halfway line on this chamber. This is such a big chamber, and it's designed to fit an entire satellite or maybe just a satellite instrument in here. Oh, can I ask teachers to keep themselves on mute, please?
I think you're on mute there, Alex.
Sorry, am I
No
am I talking now?
Yeah, you're good. Thank you.
Good. So we design and build space instruments, and we do that by we test them inside of these chambers, sometimes the big chambers, sometimes the little ones. We do research as well, so we have lots of data about our planet, and the data that comes off of these satellites we store. We develop new technologies so that future satellites can have the best technology available and create the best data for our scientists to understand. We store data and information. Data and information, they're two words that sort of mean the same thing, really. So when we store the data over many, many years, people can look back on that data and understand trends that have happened in the past. So, for example, you can look at the temperature of the oceans over decades and understand how that is changing. We have some facilities. So again, this bottom left photograph is one of our facilities. And other space companies can come to us and hire one of these chambers for a few weeks and do some testing work. And we also try to understand our economic and social impact. So we do things like this. We go to schools and we talk about our really cool science, and we support spin-out companies as well. So there's lots of things that we're doing at RAL Space. So what do I do as an engineer? Well, my name is Alex, and this is a photograph of me wearing exactly the same jumper. And an engineer is a person who has a broad understanding of science, and they use that understanding to solve problems. So you do this by working as a team. So it's impossible to build a satellite by yourself. There's so many different specialisms. You all have to work together to work as a team and create this really complicated system. So you have mechanical people, you'll have electrical people, you'll have people that are doing computer simulations, people that are making software, and all of these specialisms have to work together. Sometimes you'll need to use your maths as well to be able to solve the problems in front of you. And part of that teamwork is being able to communicate well. So our talking and listening skills are really tested. You have to understand what it is that these people are saying and disseminate information as well. And our reading and writing skills are super important as well. So if you are a person who really enjoys reading and writing, working as a team, solving problems, you enjoy science and maths, then maybe this is something that you could do in the future as well. If you wanted to get into engineering, I don't think any of you are at GCSE age yet, but if you did want to get into engineering or any other STEM related subject, then at GCSE level, you'd have to work hard at your science and your maths. If you work hard, you get good grades, then you're well on the way to having a really great career. And you might also think about your work experience. So if you have the option to do work experience, you could do it in an engineering placement. I actually did my work experience in a shop, and this was really valuable to me because I could boost my communication skills. I was actually quite a shy person at school, and I wanted to get some work experience that would help me talk to people. So that's what I did. And then in your A levels, you might think about which science you want to do, or which other subjects as well. Maths is probably the subject that will touch every career choice that you could make. So that's a really strong subject. And if you did want to get into a science or an engineering career, physics, chemistry, biology, all of these things are great. I did English as well at A level, and I did economics, and those things worked out for me. And once you finish your time at school, you might think about further steps. You could have an apprenticeship or a degree or both. An apprenticeship is a really nice thing because it's where you work 1 or 2 days a week in a college and you're learning, and then you do the rest of your working week at work, and so you get on-the-job experience. And this is for people who really like the idea of hands-on learning, so learning whilst you're doing. And the advantage of this is that you don't get any student debt because the work is paying for you to go to college. So that's a nice thing, a nice bonus. Or you might choose to do a degree, and a degree is for people who are feeling more academic, who prefer those reading and writing skill sets. I did a degree. I got a degree in physics, but it's a choice. You know, there are lots of choices in front of you, and if you start thinking about them, then that's great. So we're now going to start talking about thermal engineering. And this might be a new word for you, or a new set of words for you. But I think everybody should know what thermal means. This is a word that means sort of heat and temperature. And engineering is about designing new systems. So what we're doing is we're designing new systems and thinking about the heat and the temperature of those systems. So this picture here on the right is showing you the 3 modes of heat transfer, which you might have covered in your lessons at school, but if you haven't, don't worry. You've got 3 modes. You've got conduction, convection, and radiation. And conduction is the transfer of heat through a solid body. So you see this handle on the pan, the person is holding the handle, and further away from the pot is cooler and closer towards the pot is warmer. So as they're holding the handle, they might choose to hold it further away. And that's because heat is conducting through the handle. We also have convection. So this is transfer of heat through a fluid, and fluid can be liquid or gas. So if you have your heat at the bottom, your heat source at the bottom, then that transfers heat into the water, and the water at the bottom gets hot. And as it gets hot, it spreads out and becomes more buoyant than the cold water on the top. So the hot water will go up and the cold water will go down and fill that space that was left behind. And so the cold water starts receiving heat from the heat source, and you get this current set up as it just moves round and round. And this can happen in the pan, but it can also happen in our atmosphere, in our weather systems. Convection currents are really important if you are interested in weather. And then the final mode of heat transfer is radiation, which is the transfer of heat through electromagnetic radiation. And you can see these squiggly lines are meant to represent electromagnetic radiation. And if there was a very hot hob in front of you, without touching it, you could hold your hands over that hob and you could feel the heat coming off of it, and that's the radiation. So you got those 3 modes: conduction, convection, and radiation. And thermal engineering, it's all about understanding those 3 processes so that you can control the temperature of the equipment you're designing. Why is this important for space? Well, when a satellite is orbiting the Earth, in line of the sun, there is a lot of heat that comes from the sun, and it warms the satellite up and everything gets very, very hot, hundreds of degrees. And yet when the satellite orbits the Earth and goes into the shadow, then everything's suddenly very, very cold. That heat source is gone, and the satellite will be experiencing very, very cold temperatures. And yet all of the components on the satellite have to operate at the right temperature. And you've got to keep that temperature sort of in the middle, close to room temperature, really. So the temperature that you and I are sat in our rooms, that's the temperature that these components work best at. So if we look at this table on the left, you can see on the top row electronics. You have your electronics, and they, when you're using them, they have this operating temperature range. You need to keep them between 0 and 50 degrees Celsius. If your electronics are switched off, then you have this survival temperature range, and you have to keep them, when you're not using them, between -20 and 70 degrees Celsius. So you've got a slightly wider temperature margin. So we have to keep the temperature of the satellite sort of in the middle at room temperature to allow these things to operate, essentially. And that's really hard because the sun is so hot when you're in space and the shade is so cold. So how do we do it? Well, we have two modes of thermal control. You've got passive and you've got active. And passive control would be things like wrapping your spacecraft in a space blanket. The reason we call it passive is because there's no moving parts. It's completely unpowered. You don't have to think about it. It's just there and it works. Whereas active control would be something like a fluid moving through your spacecraft. On the hot side, the fluid gets hot and then moves around to the cold side to spread that heat load out around the spacecraft. And the reason we call that active control is because there are moving parts, there are things to think about, you have to control it really well, and it requires energy to use. So you can use a combination of active and passive, but thermal engineers really prefer passive control because there's a limited amount of energy in space. It's simpler to build, it's less likely to break, it's more reliable, it's just easier. So here's some examples of passive thermal control in nature. If you look on the photo at the left, we have some polar bears, and polar bears live in a really cold, snowy environment. So in case you didn't know, polar bears actually have black skin underneath this fur. And this fur is actually transparent, which is a sciencey word for see-through. So they use their black skin to absorb as much heat from the sun as possible so that they can get warm. And they use their fur as a blanket to trap that heat close to their body so that they can stay really, really warm when it's freezing outside. And on the right-hand side, we have fennec foxes. So fennec foxes live in the desert in really, really hot, arid, dry conditions. So they need to control their body temperatures to stay cold. And the way that they do that is they have these massive ears on their heads. And the ears are so big compared to the size of their body. What they do is they, when their body gets too hot, they will naturally put some blood circulation through their ears, and the blood will be warm and will therefore have a lot of surface area to dissipate that heat, kind of like a radiator, so they can cool themselves down that way. How is this important for space? Well, what we do is we coat all of our spacecraft and satellites in something called MLI, which stands for multi-layer insulation, which is essentially layers of shiny foil material separated by some netting material to limit the radiative heat transfer. So what this means is the foil is shiny and it reflects any radiation, electromagnetic radiation, so that it will reflect away, and the layers of the netting stop those layers of foil touching, so you can't conduct any heat through. So if one layer of foil is getting warm, then it will keep the other layers of foil cool. So every spacecraft uses MLI in some way, and yeah, that's what that is. So I'm now going to do an activity with you, and if you would like to follow along, then you can do. Otherwise, feel free to just watch. And if you are following along, we'd love to see your photos, so you can use the email address visit ral@stfc.ac.uk, or you can use the hashtag STFC Science at Home. So let's stop screen sharing for a moment. Okay, what I have some equipment with me, and I'm going to show you each piece of equipment in turn. But I'm going to tilt the camera down so that you can see my desk. Now, the first piece of equipment I have is some foil. This is just a square of tin foil, and I actually have 4 of these. Now, the other thing I have is a piece of fabric, and I have a few of these as well. In the sheet, the worksheet that you may have seen, it said you can use the netting from outside of a pack of oranges, but this piece of fabric is just as good. The next thing that I have a cool box next to me with some ice in it. There we go, get some ice in there. So I have 3 ice cubes, and we're going to go and do an experiment on these ice cubes. So MLI is multi-layer insulation, and what you have to do is one of these ice cubes is going to be our control ice cube. It will have nothing around it. Another one of these ice cubes will have our MLI on it, so it'll have lots of layers of foil separated out by the netting, and a final one of these ice cubes will just have a single layer of foil insulation on it. And sometimes we call that SLI, single layer insulation. So I'm going to do that now. So I've got one of my pieces of foil, going to grab an ice cube and wrap it up in here. So that is a single ice cube. And then the next one, that's going to have our SLI, our single layer insulation on it. The next ice cube we're going to do with multi-layer insulation. So grab an ice cube and you can wrap it up just like before. So that has a single layer of insulation on it. Then we can get some of our netting material, which for me is just some white cotton, but you might have something else. And then you can wrap that up. So that's 1 layer of foil and 1 layer of insulation. We're going to do another layer of foil. So this will be our second layer of foil. And I can already feel the temperature on this is not as cold as the ice cube in the middle. And we get another layer of insulative netting. And then we wrap that up again. You get really good at wrapping when you do this a few times. And then we get our final layer of foil and wrap that up one last time. And I'm going to put that back inside of my bowl. So now we have 3 ice cubes in this bowl. This one is plain without any insulation. This one has a single layer of insulation, and this one has 3 layers of insulation. And the idea is that the one with the most insulation will stay coldest for longest, and the one without any insulation will warm up fastest and will therefore melt. And we can see at the end of the session how these have gone. I'm going to step away from the camera for a moment and put these in a place with a bright light. I've got a sunny windowsill to put these on. So if you give me 1 moment, and I will be back in 1 minute. You can use this time to finish off your experiment and find a good sunny location to put this on. I'll be right back. Okay, my ice cubes are now resting on a windowsill, and that means that we have some time to go through the worksheet. So you might have a copy of this worksheet. If you don't, it doesn't matter, because I'm going to go through it anyway. So I'm just going to share my screen. So hopefully you can see this worksheet. Let's have some water as well. Okay, so the worksheet starts with a question: is space hot or cold? The answer is it's both. There are patches of space filled with gas that can be millions of degrees Celsius. It's really, really warm. And there are patches of space that are empty, that are close to the temperature absolute zero, which is the coldest temperature in the universe. So space is both hot and cold, and the spacecraft that we have to design have to put up with these temperatures some way or another. So we now have this discussion about heat and temperature. Are they the same thing? And the answer is no. Sometimes people use the words heat and temperature interchangeably, but actually in science, they have a very specific definition. So I am going to go through some questions with you. I'm not sure if I can see the chat function, but if teachers wanted to put answers in a chat function, students can put your hands up and talk to your teachers. And hopefully,
Alex, I can ask you the questions that they've asked in the chat already.
oh, yeah, I don't see the chat function when I'm sharing my screen. Sorry.
I know it's hard to see when you're sharing your screen. No, that's okay. We can just go through them here. So one student asked, why do the scientists need to wear protective gear when working on the satellites?
Oh, okay. So we're not protecting the scientist here. We're protecting the satellite. So the satellite has to be kept really, really clean. So we call these rooms clean rooms. And you'll be losing, skin cells from your arms or clothing fibers or hair all the time. So yeah, you're protecting the satellite from getting dirty, essentially. Actually, that's a really good question. Maybe we can have the questions from the chat at the end. If we have the answers to these questions, I'll read them out first.
Great.
And then, so question 1, heat is a form of A, radiation, B, energy, or C, light. So if students can talk to their teachers and the teachers can type what they think the answer is in the chat function, and maybe you can tell me what answers are starting to come through.
Yeah, absolutely. I see 2 energies. There's a few questions sprinkled in here. Teachers, if you could just for now answer these questions, that would be fantastic. I see a B. Mostly saying energy.
Yeah, all of those answers are right. So yes, the correct answer is B, energy. Heat is a form of energy. And you can think of energy in terms of heat or light or movement or electricity. They're all different types of energy. Question number 2, heat is measured in A, Kelvin, B, joules, C, calories. I wonder if there are any answers filtering through for this question.
I'm seeing Kelvin, B, Kelvin and B. Someone said joules.
Yeah, some of these answers are right. So the answer is B, joules. Kelvin is actually a measure of temperature. And it's kind of a trick question because you can have B or C is technically correct. You can imagine the word calories. You might recognize this from food. Calories is another way of measuring energy, but you're measuring food energy. So if you're a chef or a food scientist or a dietitian, you'll be measuring energy in calories. But in space science and technology, you're actually measuring energy in joules. So the answer is B. And then question number 3, Temperature is a measure of how blank a substance is and is calculated as the blank of particles moving in it. And the answers we can have are A, hard or soft density, B, dark or light speed, or C, hot or cold speed. So
I'm seeing some C's, all C's for now.
yeah,
Yep,
The
still
right-
just all coming through as C's.
yeah, that's the right answer. So temperature is a measure of how hot or cold a substance is, and it's calculated at the speed of particles moving in it. Just absolutely right. So next we have this discussion about the difference between energy and temperature. And you can imagine you've got a bucket of water in front of you, and it's at 25 degrees Celsius. Imagine in your mind's eye this bucket of water, and it's at room temperature. If you put 5,000 units of heat into this bucket of water, and it's written in a very confusing way. Units of heat, I think, is put on the sheet so that we're not using the word joules, which would give away the answer to question 2. So we put 5,000 joules into this bucket of water, and it raises up by a degree Celsius. Well, if you compare that to a smaller volume of water, this one's just a cup. If you start off with a cup of water that's at room temperature and you put 5,000 joules in it, suddenly it raises up 10 degrees Celsius. So the same amount of heat has gone into this, but because there is a smaller amount of this stuff, a smaller amount of water, then the temperature has gone up a larger amount. And then if you imagine again, we're going back in our mind's eye to this bucket of water. If it starts at 25 degrees Celsius, again at room temperature, this time you're putting in 20,000 joules, suddenly the temperature goes up to 29 degrees C. What this means is if you compare it to our first example, where we only went up 1 degree C, you put in more energy to the same amount of stuff, then the temperature goes up more, which kind of makes sense if you think about it. Our next section of questions is all about conduction, convection, and radiation. And we've got some pictures on the worksheet to help the students find the correct answer. So question number 4, conduction is the transfer of energy between objects. And I'm going to label this answer A, in physical contact, answer B, in close proximity, or answer C, immersed in water. So A, B, or C? And answers in the chat function, please.
I'm seeing all A's right now.
Yeah, that's
Yep,
correct.
still all A's.
So in physical contact is the correct answer, and you can look at this picture, which helps you find the right answer. The next question, 5. Convection is the transfer of energy between an object and its environment due to, we've got A, electromagnetic waves, B, kinetic energy, or C, fluid motion. And again, look at these images to find the answer. If there are any answers coming in.
C's. We got 1 B, mostly C's though.
Okay. Yeah, the correct answer is fluid motion. So if you imagine the gas above this candle is the air, that is a fluid. And then our final question, radiation is the transfer of energy by A, magnetic fields, B, electromagnetic waves, or C, objects in physical contact. Any answers coming through for this?
B, electromagnetic waves. I got 1 A, mostly B's.
Yeah, that's correct. B, electromagnetic waves. So if you look at this image, you can see the waves coming off from the light source, and those are electromagnetic radiation. Then we've got this discussion further down the worksheet of how heat is transferred in space. Actually, there is no fluid in space because it's a vacuum. So the only way that heat can reach us from the sun is through electromagnetic radiation. So all the heat is transferred by electromagnetic radiation. There is the possibility of conduction in space, because if you have one part of your satellite getting hot and another part of your satellite is connected to it, then it can conduct along the length of the satellite, but mostly it's radiation. So now we've got this discussion about space telescopes, which goes on for a little bit, but essentially there's lots of space telescopes orbiting the planet, but the ones you might have heard of are Hubble and the James Webb Space Telescope. So they orbit the planet and they look out into space and take amazing pictures of the universe. So if you've seen those pictures of nebula or stars or galaxies, those are all taken by space telescopes. Hubble is the space telescope that's currently in operation, which is on the right-hand side of this picture here at the bottom. But it's been in operation for 30 years, and technology has moved on since then. So the James Webb Space Telescope is going to be replacing Hubble. And what's cool is that this James Webb Space Telescope has a mirror on it that is many times bigger than the mirror in Hubble. So that means you can get much more detail in your image, in your photographs that you're taking. So it says here, Webb has a much bigger mirror than Hubble, 6.5 meter diameter compared to Hubble's 2.4 meter diameter. You can essentially see better detail, or you can see further into the image field. James Webb Space Telescope has 4 different instruments on it, but the one that I'm going to talk about is MIRI, Mid-Infrared Instrument. And RAL Space, where I work, actually tested this instrument and made sure it was working. So that was part of the work that we did in partnership with NASA. So that's very cool. So
Just
then
a heads up, Alex, we have about a minute left.
Okay. In that case, we've got this discussion about MLI, but we've more or less covered that in the presentation. So our next part is the challenge, which hopefully you are following along with. And I'm going to go and check on my ice cubes and bring them back, and we can compare the sizes of those. So I will be back in a minute.
Great. Just in the meantime, students and teachers, I'm going to put some polls in the chat. If you wouldn't mind just filling those out for whatever the majority of your students say, that would be fantastic. I'm also just in a minute going to post some feedback forms for you to please fill out for you and your students. And then also next week, we have our Accelerator Week, which we will have lots of very exciting brands coming in and speaking about how the curriculum relates to their jobs. So if any of your students are interested, please have them sign up for that. I'll go ahead and post that sign up link in the chat as well.
Okay, I've just come back. Just to wrap up our session, I'm going to show you my bowl of ice. And you can see we've got this ice cube which didn't have any insulation on it. This is already starting to melt. It's surrounded in a pool of water. And we're going to start unwrapping our ice cubes. So I'll start with the one that is wrapped in a single layer of foil. I can feel the foil is very cold on my hands. So it's starting to conduct the temperature, the heat. And as I open it and pour that bit of ice out, you can see this ice cube is marginally bigger, so it hasn't melted quite as much. And then our final ice cube, which is wrapped in some soggy cotton and layers of foil. As I unwrap it, the outer layer of foil was actually not very cold, but as I unwrap it, the inner layers are starting to get colder. So tip that one out. And you can see This, oh, that's the camera. This one is clearly bigger than the other two. So our experiment was a success. We've learnt that different layers of foil, as long as they're separated by this insulating material, keeps the ice cube colder for longer because it's reflecting the heat away from the ice and keeping conduction down to a minimum. So I wrapped that up a bit quickly at the end there, but I hope that was good and fun and people learnt a lot.
Absolutely. Thank you so much, Alex, and thank you, students and teachers, for your participation. This was a really fun session.
Good. In that case, I will leave the meeting.
Thanks.
Thank you. Goodbye, everybody.
Bye.